Prediction of an outcome is an important factor in sciences and in real life, and one of the basic ways to predict the future or an outcome from available information is by performing regression analysis. Regression analysis is a type of predictive modeling that specifies the dependent variable as a function of the independent variable. That is, regression analysis is a statistical tool used for analyzing the relationship between the dependent and independent variables for the purpose of making predictions. Regression analysis includes several variations such as simple linear regression analysis, multiple linear regression analysis, and nonlinear regression analysis, among others. But in this video, I will be demonstrating how to perform simple linear regression analysis in SPSS. Please endeavor to see this video to the end. My name is Titocan, and this is Titocan Max Solutions, a YouTube channel for improving the knowledge of how to do things. If you have not subscribed to my channel, please kindly do so now by clicking on the red subscribe button below, and by doing so, you have encouraged education and learning. Simple linear regression analysis is the most commonly used type of regression analysis, and it is used anytime the dependent variable is a linear function of the regression coefficient. That is, linear regression is a statistical procedure which consists in the use of one independent variable and one dependent variable to produce a model that assesses the relationship between two variables in a linear fashion for the purpose of making predictions. And this procedure is made easy in SPSS. The simple linear regression model is usually expressed as y equals mx plus b, where y is the dependent variable or the outcome, x is the independent variable or the predictor, m is the slope or the coefficient, and b is the constant term or the y-intercept. And our simple requirement in performing linear regression analysis is to determine the slope m and the constant term or the y-intercept b in the equation so that it becomes a useful model. However, there are some assumptions your dataset of variables must satisfy in order for the output to be valid. The assumptions are: 1. Your dependent and independent variables should be measured at the continuous level. That is, they should either be interval or ratio variables. 2. There should be a linear relationship between the two variables. That is, the correlation between the two variables should not be 0. 3. Your data should exhibit homoscedasticity, which means the variances in your data along the line of best fit should remain similar as you move along the line. 4. Your data should have independence of observations. 5. There should be no significant outliers in order to protect the residual and make the prediction outcome valid. And 6. The residual or errors of the regression line should be approximately normally distributed. If any of these assumptions is violated or not met by your data, the result of the simple linear regression analysis may not be valid. In this case, you may have to go back into your dataset and do some corrections where necessary, and then return to perform the regression analysis. On the other hand, you may be required to perform a nonlinear regression analysis instead, should your data be badly conditioned. So it is important to test your data for these assumptions and ensure they are tenable before you progress to assess the regression results or use the model. Now let's take a look at the data for this demonstration. This is our set of fictitious data created for the purpose of this demonstration. It is already loaded into SPSS and it consists of the independent variable feeds, which actually represents the number of times feeds were administered, and the dependent variable weight, which is the weight gained. The sample size or the number of cases for the variables is 30. To learn how to load data into SPSS, please see my previous videos on Introduction to SPSS Software for Beginners, Part 1 and Part 2 to learn more. Now let's go into SPSS and get started with the demonstration. First, Let's be sure that the data we are using satisfies all the required assumptions by putting the dataset to test for the assumptions. The test for assumption number 1, 2, and 3 will be performed outside the regression analysis procedure, while assumption number 4, 5, and 6 will be performed simultaneously with the regression analysis. Assumption number 1 is simple to test. As you can see, the feeds and weight variables are both continuous scale variables measured at interval ratio level, which satisfies assumption number 1. Assumption number 2, which is the linear relationship between the variables, and the assumption number 3, which is the exhibition of homoscedasticity by the data, can both be tested simultaneously using a scatter plot with overlaying regression line. Now, let's perform the test for assumption number 2 and 3. Go to the menu bar and click Graph, and from the sub-menu, click Chart Builder. Click OK on this Chart Builder information box to open the Chart Builder dialog box. Now, click on Scatter Dot from the box on the lower left corner to display various scatter plot in the gallery. And from the gallery, click on Simple Scatter and drag it to the canvas like this and drop it. Then, from the box on the upper left corner, click on the independent variable feeds and drag it to the x-axis and drop it there. Then, click on the variable weight and drag it to the y-axis and drop it there. Then, click OK to produce the scatter plot. Now, let's add a regression line to this scatter plot. To do this, double-click anywhere on this scatter plot to open the chart editor. In this chart editor, click on this icon that is called Add Fit Line at Total, and then close the window to update the scatter plot with the regression line as appropriate. As you can see, the dots go up to the right as well as the regression line, which suggests a positive linear relationship between the dependent and independent variables. This means there is a linear relationship between the variables as required by assumption number 2. As you can also see, the dots are generally scattered or distributed about the regression line as you go up to the right with relatively equal variances, and this suggests that the data exhibit homoscedasticity as required by assumption number 3. So, to this extent, we have established tests that satisfied 3 assumptions so far. So, the test for the other 3 assumptions will be determined in the regression process. Now, go back to the menu bar and click on Analyze. From the sub-menu, put the cursor on Regression, and from the drop-down options, click on Linear, and the Linear Regression dialog box opens. In this dialog box, you have your data in the box on the left. At the upper right, there are 2 relevant boxes, that is the dependent box and the independent box. In this video, I want to use the feeds to predict the weight. So click on the independent variable feeds and then click on this transfer arrow key to move it to the independent box. Thereafter, click on the dependent variable weight and then click on this transfer arrow key to move it to the dependent box. Leave the default method as enter. At this point, you can click OK and the regression results output will be produced. But there is need to make additional selection of statistics and plot in order to also test for the other assumptions. So click on the Statistics button to open the Linear Regression Statistics dialog box. In this dialog box, the estimates and the model fit boxes have already been checked by default. In addition, check the box for confidence intervals and ensure the level is set at 95%. This selection will ensure the model outputs are produced at 95% confidence intervals. Then check the box for descriptives. This selection will produce a table of the mean, the standard deviation, and the sample size of the variables. Then check the box for Dubbin-Watson. This selection will provide the test result that will be interpreted to check whether the variable satisfies the assumption for independence of observations, which is assumption number 4. And then check the box for case-wise diagnostics. This selection is to actually test whether the data satisfied assumption number 5. That is, whether there is outliers or not in the dataset. If there is outlier in your dataset, this selection will produce a table containing list of cases of outliers. But if there is no outlier in your dataset, the case-wise diagnostic table will not be produced. After you have checked the necessary boxes like I have done, then click Continue to close this dialog box. Now, click on the plus button to open the Linear Regression Plus dialog box. In this dialog box, transfer the zpredict written as zpred to the X box, and then transfer the zresidual written as zresid to the Y box. Then check the boxes for histogram and normal probability plot respectively. This plot selection will help to determine whether the size of the residual is constant across the entire dataset or not. Selection of the histogram and the normal probability curve is to determine whether the regression residual or error associated with the model is approximately normally distributed or not. This plot will check for assumption number 6. Then click Continue to close this dialog box, and then click OK to produce the regression results in the output window. Now, before we proceed to interpret the results, let's check whether the data satisfy the remaining 3 assumptions. The test for independence of observations was performed using the Dubbin-Watson test statistic. Now, proceed to the model summary table and check the Dubbin-Watson statistics column. Generally, independence of observations will be tenable if the Dubbin-Watson test result is not less than 1 or greater than 3. Here, as you can see, the Dubbin-Watson test result is 2.737, which means the assumption number 4 is tenable because the data has independence of observation. Because regression is very sensitive to outliers, the test for outlier is determined by the use of standardized residual interpreted like a z-score to check for outliers in regression analysis. Now, proceed to the residual statistics table. Generally, the minimum standardized residual should not be less than -3.29, and the maximum standardized residual should not be greater than +3.29. If they do, then there is outlier in your dataset. Here in this table, the minimum standardized residual is -1.932, while the maximum standardized residual is +1.622. This means there is no outliers in the dataset, and so the case-wise diagnostic table is not produced. This means assumption number 5 is satisfied and tenable. Assumption number 6 was tested by using the histogram and the PP plot. As you can see, the histogram and the overlaying normal curve look like a bell shape, and the normal PP plot of the regression standardized residual are closely distributed along the 45 degrees fitted line. These two plots looking like this respectively show that the residual is approximately normally distributed. Suffice to say, the assumption number 6 is satisfied. To crown it all, this scatter plot of the standardized predicted value against the standardized residual is simply the residual plot, and it is specifically to also check whether your data exhibit homoscedasticity as required in regression analysis. This plot is useful to see whether the size of the residual is constant across the dataset. If it is not constant, then this data exhibits heteroscedasticity, which will mean something is wrong with the dataset. But as you can see, this scatter plot is elliptical, have zero pattern or relationship as expected, and therefore the size of the residual is constant across the dataset. So the data is homoscedastic. So all the assumptions have been met. There is nothing to transform or fix in the dataset, so the data was qualified to be used for regression analysis. Now, we can proceed to interpret the regression analysis results. Let's proceed to the first table. The first table here is the descriptive statistics. This table gives idea of the mean, the standard deviation, and the number of cases of the variables. Such information is important to be known. The second table is the correlation matrix. The Pearson correlation shows that the variables correlate at 0.849, which shows a very strong relationship between the dependent and independent variables. The third table is the variable entered or removed. This table tells us that the only predictor in the model is fits applied as enter method, and the dependent variable is weight, which confirms that we are performing simple linear regression analysis. The fourth table is the model summary table. In this table, there are some useful information. The capital R, which is the correlation coefficient, is given as 0.849, which was the same value in the correlation matrix table. Then, the R square, called the coefficient of determination, which is the proportion of variability in the outcome variable accounted for by the predictor variable. The R square is given as 0.721, and since it is interpreted in percentage, we multiply it by 100. This means 72.1% of the variance in weight gained is predicted from the feeds administered. But please note that some authors or statisticians use the adjusted arrow to mean the same thing instead of using the arrow square. The fifth table is the ANOVA table. ANOVA is present here because ANOVA and regression are also part of the general linear model. So in this case, the ANOVA result tells us whether the model works or not, by indicating whether the predictor is significant or not. That is, it indicates whether the model with one predictor significantly works better than using the mean value. As you can see, the significance level or the p-value is less than 0.05, which means the predictor is significant. Suffice to say, the model with one predictor will satisfactorily predict the dependent variable weight. That means there is a statistically significant relationship between the predictor and the outcome variable. If the p-value was greater than 0.05, that means the choice of the predictor in the model was not significant, and the predictor will not produce the outcome better than just using the mean value. But in this ANOVA table, the p-value is 0.000, which is less than 0.05. This means that the predictor in the model is significant, and this tells us that the model works. Now, the sixth table is the coefficient table. This is a very important table in regression analysis because this table tells us how the model works. Remember, the model equation is given as y equals mx plus b, where m is the slope or the coefficient value, and b is the constant term or the y-intercept. So this table provides the constant and slope values for the regression model. So our main concern in this table is the column B under the unstandardized coefficients. As you can see, the constant value under the column B is 71.960, while the coefficient value or the slope value is 8.068. When you fit these values into the regression model, you will have y equals 8.068 multiplied by x plus 71.960. This model means for every 1 unit increase in feeds administered, the weight will increase by 8.068. Another important element in this table is the 95% confidence interval for the unstandardized coefficients B. The lower and upper bound show that for the coefficient or the slope to predict weight from feed, the range is from minimum of 6.127 to maximum of 10.009. That means for each unit of increase of feeds administered, weight increases by 6 to 10 points in relation to the negligible error associated. Now, since we have our coefficients M and B, let's now use our regression model to make predictions as required. Let's predict the weight of fish if feeds are administered at the following times. 1. 20.5 times. 2. 30.5 times. And 3. 40 times. The way to apply the model is to substitute for x in the equation the number of times the feeds are administered. Your result will be as highlighted in the table. If you administer the feeds 20.5 times, the weight output would be 237.4 kg. If you administer the feeds 30.5 times, the weight output would be 318.0 kg. And if you administer the feeds 40 times, the weight output will be 394.7 kg. As you can see, for every unit increase in the number of times feeds are administered, there is a corresponding increase in the weight gained. This is expected because there is a positive correlation between the dependent and independent variables. This is how to perform regression analysis in SPSS. If you have any question, please leave it with me at the comment section. But right now, we have come to the end of this video, and I hope you will be able to replicate the procedure as demonstrated in this video to perform regression analysis of your data in SPSS. If you like this video and you want to see more video contents like this, please give this video a thumbs up and please subscribe to my YouTube channel so that we begin to send you notifications every time I publish new and useful content. Subscription is free. Thanks for your time and subscription, and I hope to see you again in my next video. Bye.